This lecture is on the chain rule. Let me write it down, kind of prove it, and then do a bunch of examples to illustrate its use. It is probably the most important of all of the differentiation rules that you can possibly imagine. This is the one that's going to take us through what we need to do as far as derivatives are concerned for the rest of a calculus sequence. This is the big one. So, put a big stars around it, whatever you got to do. This is huge. But it looks bad at the beginning. Let me write it out. It's called it is a theorem, and it says this: if g of x is differentiable at a, and f of x is differentiable at g of a, then the derivative of f circle g of x equals, at a, equals f prime of g of a times g prime of a. We'll talk about the particulars here in a minute, but you should recall, when you see something like f circle g of x, that is the composition of f with g. That is written as f of g of x. So, with that in mind, this is a statement about composition of functions. G can be called the inner function. Let me see if I can do that here. We would call g the inner function. And f we would call the outer function. And it's used to handle more complicated derivatives than we have at our disposal right now. So, let me box this out of the way and show you roughly how the proof works. So, let me start with f circle g prime of a. So, f circle g prime of a equals the limit as x goes to a, f circle g of x minus f circle g of a all over x minus a. Now, to make things a little more familiar with you, I'm going to go away from this circle notation and rewrite this as the limit as x goes to a, f of g of x minus f of g of a all over x minus a. So that's the definition. Now, the trick that's usually done in these kind of problems is this. I will simply multiply and divide by g of x minus g of a. Something of a trick. And then rearrange things and have f of g of x minus f of g of a over g of x minus g of a times, and then I'll have g of x minus g of a all over all over x minus a. And then at this point, you're allowed to break up the limits so long as all these limits exist. So I'll have the limit as x goes to a, f of g of x minus f of g of a all over g of x minus g of a times the limit as x goes to a, g of x minus g of a all over x minus a. Now it's at this point where you want to express some excitement, seeing that this right here is g prime of a. So the part before it, all of this stuff, must be f prime of g of a. It's got to be, otherwise the theorem wouldn't be true. Unfortunately, there is a lot of complication right there. For one thing, this thing here is not g of x goes to g of a, now is it? In order to have this work, I need this down here, x minus a, x goes to a. G of x minus g of a, I should have g of x going to g of a. And I'm not going to be able to do that, especially if, for example, g of x happens to equal g of a for, I don't know, an infinite number of terms. Let me show you how that could possibly work. When we do this, we say x goes to a, and we're guaranteeing that x does not equal a while this process is going on. However, it's possible that while the x may not equal a, whatever g is, g of x could be equaling g of a for a lot of points. Let me give you an example. Suppose g of x, this is just an example to show you what I'm talking about. Suppose it equals a constant. Well then, g of x minus g of a equals 0 for all x and for all a. So I could never have done the little trick that I did where I multiplied and divided by g of x minus g of a. And not only that, if I wanted to exchange that, if I want to even think about this, the limit g of x goes to g of a, f of g of x minus f of g of a all over x minus a, you have to guarantee me that I can get an interval around a, g of x minus g of a, you're going to have to guarantee me an interval around g of a for which g of x does not equal g of a on that interval. That's how the definition of the limit works, and you can't guarantee that. So with this kind of stuff happening, I can't even begin to do it. That's kind of what happens in the other cases. Most cases that we'll deal with in this book, outside of a few very strange ones, this is we'll be okay with what we do here. I mean, that's basically the idea. But to be honest, if you actually read the proof, it'll be in your book, it'll be on the web, wherever. The part that I did here is the easy part. The hard part is dealing with this stuff. But I don't think it's very beneficial for this particular class. So let's do some examples. There are a couple of notations that you might want to be aware of. Let's take a look. The chain rule comes in two flavors. It looks like this. Let me write the symbolism for it. One is f. You'll see various things here. You might see f circle g prime of x equals f prime of g of x times g prime of x. You might see something like f of g of x. I don't want to put the prime here because that means I'm taking the derivative of f. So you might see something like prime That's horrible, but that happens. F prime of g of x times g prime of x. That could happen. There's a Leibniz version of it too. If you have more than one function floating around, dy over dx equals dy over du times du over d of x dx. In order to make this happen, I have to assume that u is a function of y, and that x, or y is a function of u, and that u is a function of x. So what I'm going to do is I think I'll use this method here because it's good for beginners. And I'll change to this kind of stuff up here because it's faster the better you get at this. As an example, determine dy over dx for y equals cosine to the fifth x. Alright, so in order to make this work, I need to think of y as being part of an inner function and an outer function. So remember, y equals cosine of x to the fifth power. That 5 that's put between the s and the x up here, that's a convenience. So that, I guess you can save parentheses by not writing that. Anyways, here's the way it works. Consider your inner function. The inner function that would be this guy in here, cosine of x. U equals cosine of x. Okay, and the outer function, see, in this notation here, it's hard to see an outer and inner based on what you're looking at. But here you can definitely see there's an inside and an outside. The outer function is y equals x to the fifth. So now let's see how this works. I have u equals cosine of x, so du over dx equals negative sine of x. Now y equals u to the fifth. I probably should have said, yeah, back here, this is going to be u to the fifth because it's cosine to the fifth. So y equals u to the fifth. Then dy over du equals 5u to the fourth. So then dy over dx equals dy over du times du over dx. dy over du is 5u to the fourth. Du over dx is negative sine of x. And now I'll plug in what I had for you. U is equal to cosine of x, and I have 5 cosine to the fourth x times negative sine x. You can leave the answer like that, but maybe some people will write something like this instead. Negative 5 cosine to the fourth x sine of x. And maybe leave their answer like that. Let's do another one. Sort of a reverse of the previous example. What about this? Y equals cosine x to the fifth. This does not mean cosine of x to the fifth power. This means y equals cosine with x to the fifth on the inside. So now x to the fifth is the inner, and cosine is the outer. So the inners are u. U equals x to the fifth, and the outer function y equals cosine of u. So du over dx equals 5x to the fourth. Dy over du equals negative sine of u. And so our answer, dy over dx equals dy over du times du over dx. Dy over du was negative sine of u. And then du over dx is 5x to the fourth. And then I will replace my u with the x version. Negative sine of x to the fifth times 5x to the fourth. If I have y equals e to the x cubed, do you know how to think of this in terms of an inner and an outer function? For example, raising something to a power, what's on the inside? Well, some people write it this way, exp, and put the x cubed in parentheses. That way it's easy to tell what the inner and the outer function is. The inner function is x to the 3, and the outer function is e to that. So, my inner, u equals x cubed, and my outer, y equals e to the u. So then du over dx equals 3x squared, dy over du equals e to the u, and so dy over dx equals dy over du times du over dx, which equals dy over du e to the u times du over dx, 3x squared, and I'll replace u with x cubed, so I get e to the x cubed times 3x squared. How about y equals x squared plus x plus 1 to the 10th power? Well, it's easy to tell what's inside and what's on the outside here. The inside is the x squared plus x plus 1, it's the inner. And raising to the 10th power is the outer. So u, my inner function, is x squared plus x plus 1. And then du over dx equals 2x plus 1. Y equals u to the 10th. Dy over du equals 10u to the 9th. So dy over dx equals dy over du times du over dx. Now, as I write this every time, I suggest you do that too. After a while, it will become something that you do by rote without thinking that you've memorized it. So give it a try. Write it every time. Take a little more time to do your homework and do that. It'll yield great dividends. All right, so dy over du was 10u to the 9th, and then du over dx was 2x plus 1, and u, okay, so 10 times x squared plus x plus 1 to the 9th times 2x plus 1. I'm going to go to something else now. The other notation looked like this. The other form of the chain rule said f circle g prime of x equals f prime of g of x times g prime of x. And I'll be honest, this is the version that I use when I'm working, especially large problems, and I have to do a lot of differentiating on the fly. And the Leibniz notation, the dy over du, all that stuff, starts to run into major complications when you have more than one function inside of another function. I mean, if you've got a function inside of a function inside of a function, it starts to get pretty tough after a while to keep track of everything. You've got to give everything different names. Anyways, let's do this. Y equals e to the square root of x squared plus 1. See, now if you look at this, e is the outer, now it's not just the outer function, but it's the outermost. And then the square root is the next outermost. And then the x squared plus 1 would be the inner. See, this is just not going to be that great. It's not that bad. I mean, really, it isn't. It's just, if you keep, as long as you keep all of your U's and B's or whatever letters you do in the right spots, you'll be okay. It's a lot like dimensional analysis, where you try to get like feet per second squared, and then you multiply by something to take out seconds or something like that. It has a very similar feel to that. And it makes sense because derivatives are rates of change. But here's the way I do it. I went dy dx. E is the outermost function. That's true. What is the derivative of e to the x? The derivative of e to the x is e to the x. So this is e to something. I just say, I leave it alone, because e to the something, the derivative is e to the something. However, times the derivative of what it was e to. Square root x squared plus 1. It's easy to tell which one is coming next, because now the square root is outside of x squared plus 1. You simply copy what you had before, times. Since the outer function is the square root, I think of what is the derivative of the square root function. It is 1 over 2 square root. And now I'll just copy what was inside of there. Now, that had a function inside of it as well. So I will do d over dx of x squared plus 1. I stop there because I can take the full derivative of x squared plus 1. So I'll have e to the square root of x squared plus 1 times 1 over 2 square root of x squared plus 1. The derivative of x squared is 2x. And as I've mentioned before, you can leave your answers like that. I'm perfectly happy with them. Although if you want to go about simplifying, I'm not going to be mad about that either. You can see I can take these 2's out of here and out of here, and I'll have an x and an e to that stuff in the numerator. So I'd probably write this way. X times e to the square root of x squared plus 1 divided by the square root of x squared plus 1. In a way, you can see how a lot of things are related to each other that way. Here's another function inside of a function inside of a function. So when I start taking my derivatives, I work basically from left to right unless it's an exponent. So I still do actually left to right even if it is an exponent. But whatever the case may be, the first one I'm going to attack is sine. What is the derivative of sine? It's cosine. And I leave the interior alone, or the inner functions alone for now. When I take my next derivative, it is the derivative of the stuff that was inside of the sine function. See, basically I'm peeling away one function at a time until I get to the end of this thing. So perhaps the most painful portion of this is writing all this stuff so many times. My next function in line is cosine. The derivative of cosine is negative sine. And I'll leave the 1 minus x cubed be. But I will take the derivative of 1 minus x cubed. Finish it off, cosine of 1 minus x cubed. Just make sure you get your parentheses right. I have a parenthesis here and a parenthesis here. That's 2 open ones, so I need 2 of them to close it up. Now also, I see I have a negative here. When I take this derivative, it's going to be negative 3x squared. So I'm going to forget about that negative. And if you leave it in that order, I suppose you can kind of see the derivative as it happened. This one here has a fraction inside of a power. So when I do the derivative, the outermost function is raising to the 10th power. So I'll have 10 parentheses to the 9th, x cubed minus x plus 9, all over 3x squared plus 5 times the derivative of that fraction. And of course, the way those work, let me give myself a little extra space here. This is the last derivative I have to do because there's nothing inside of anything here. It's written in terms of x itself. So I can have, using the quotient rule, d over dx, x cubed minus x plus 9 times 3x squared plus 5 minus x cubed minus x plus 9 times d over dx 3x squared plus 5. All of that is over 3x squared plus 5 squared. Let me go ahead and put in my derivatives. I have 10 times x cubed minus x plus 5 plus 9 all over 3x squared plus 5. This guy here is going to be 3x squared minus 1 times 3x squared plus 5 minus x cubed minus x plus 9, and the derivative of this piece here is 6x. And all of that is over 3x squared plus 5 squared. So these can come in all sorts of different forms. Here, this one was a quotient rule inside of a power rule. You would have, try some other rules out. I'm sure I'll assign the problems where you'll have a product rule inside of something like that. The last problem I'd like to take is one that I've put on many exams, although I didn't mean to put it up there. I'm giving you values for the function and its derivative, and for g and its derivatives. And then what I have here are a bunch of different rules. Well, this one right here is just a straight up quotient rule, which I'll do that one, I don't care. But here is a chain rule, and over here is another chain rule, because you've got f of x is inside of the square root, which is inside of g. So let's see how these all work. For part A, we know that since we're doing a quotient, the quotient rule says we do f prime of what? F prime of 3, leave the bottom alone, minus f of 3 times g prime of 3, and in the denominator, g of 3 squared. So let's throw these numbers in. F prime of 3, 7. G of 3 is negative 6. F of 3 is 4. And G prime of 3 is negative 9. G of 3, the was negative 6, that's right. Divided by negative 6 squared. And so that equals negative 42 plus 36 over 36. So it looks like negative 1/6. Negative 6 over 36 is 1/6. Next, we want d over dx. So we want f prime of g of 3 times g prime of 3. That equals f prime. I got to figure out g of 3 and g prime of 3. So let's start with g of 3. G of 3 was negative 6, and then g prime of 3 was negative 9. And then finally, f prime of negative 6. Let's see, there it is. Prime is negative 5. So that equals negative 5 times negative 9 equals 45. Oh. Let me see, we want, for C, let me see if I can sneak it in here. For part C, I'm going to have g prime of the square root of f of 3 times the derivative d over dx. I'm not sure I don't think I'm going to do that. No, because it's going to get way too complicated here. The next thing I have is the square root. So I'm going to get 1 over 2 radical f of 3. And then the last thing that's inside is f of 3. So I have times f prime of 3. Now let's take a look at the numbers. Start with f of 3, that's 4. So I'm going to get g prime, the square root of 4. And f of 3, I already know is still 4, so that's times 1 over 2 radical 4. And then f prime of 3 was 7. And so now g prime of 2, where's g prime of 2, is 8. The fact that it's there gives me a lot of confidence that I'm doing this right. We have 8 times 1 over 2 radical 4. Get caught up in the moment. Take out this and this, I'll end up with 14.